thank you very much. Thank you very much for the introduction. And I'd like to thank the organizers for the invitation and to this great conference. I'm honored to be, really honored to be a speaker here. And I'd like to thank Ellen, and I am really honored that I have written 2 joint papers with Ellen, and yes, through this collaboration, I learned a lot, and yes, the Ellen shared very kindly shared the interesting problems and interesting ideas and perspectives with me, and so I learned a lot. And she is also very kind and patient to listen to my ideas, which are sometimes silly, but anyway, thank you very much. The title of my talk is Weight Filtration on Log Crystalline Sites. Yeah, Professor Iruji advised me to put S here, but okay. In this talk, so I will construct a weight filtration, weight filtered object, construct a weight filtered object on certain log crystalline sites, which induces Mokrane's one. Yes, Mokrane and Nakkajima's one. And I explained my setting, and P will be a fixed prime. And I start with a base log scheme, S log. This is a pair, and S and N, curly S. And this is a log scheme on which P is nilpotent. Such that N is associated to the monoid, monoid homomorphism to N to O carry S, which sends 1 goes to 1, which sends 1 to 0. So I consider hollow log structure. It's a kind of family of log points. And capital S log, this will be S, capital S and N inside S carry S log. And this is an exact closed immersion. So I write also the log structure of capital S log by N by the same letter, because it's a pullback of the one in curly S log. And yes?
Could you wait the first line, because it is in the dark here? First line on this one border.
It's invisible, yes.
Yeah. Thank you very much. I apologize.
No. And with because we want to discuss a crystalline site, we need a log structure and a PD structure. I'm sorry, PD structure on kernel of the curly O curly S to the curly O capital S. Okay, then now it's not, okay. X log, this is XM to the S log, and I will warn you that I wrote this L in the capital letter and this L small letter, okay? This is a family of simple normal crossing log varieties. And this, by this I mean
sorry, maybe this, I'm not sure whether there are some compatibility between the PD structure and the log structure.
No.
Okay.
And yes, the definition of the family of simple normal crossing log varieties is that X is a union as a scheme of xi's, and xi's, each xi with a class trivial without log structure. It is smooth over S, and Zariski locally on X F. Oh, I forgot to write F. I'm sorry. F is associated to the following diagram. To the OX, which is O smooth over OS x1 to xm divided by the product of x1 to xm, and which is admits a natural morphism from OS, and this is a natural one, and we had a log structure, so the log structure n is associated with that one, and we have the nm to x, and here this is a diagonal map, and here the i's canonical basis is mapped to the image of xi in here. And we assume that this is the definition of my definition of a family of simple normal crossing log varieties. I think this is the terminology of Nakkajima. And so here, as I just warned you, here is my rule for the superscript, and when we consider log structure n or something isomorphic to n, I write small l, small o, small g, and I write consider the log structure, put the log structure m on x or something isomorphic to m, I use a big L and small o, small g, and I sometimes call it this a small log and a big log.
But the diagram here describes only the maximal crossing points, right?
Smooth.
For example, if you take a smooth point of xi, which does not meet, a point in xi which does not meet the other xj, then this description is not the one you mean.
No. For example, the locus where this is like this. So this is like this, and so here.
Maybe the terms are not the same in general.
Yes, but I would like to write like that because I don't say that the image of this map it contains the origin. So, for example, so but we can use different set of indices, but okay. I'm sorry for but I wanted to first fix the reducible smooth components, so smooth components, yeah. And then for j inside the index set 1 to m, we write as usual the xj to be the intersection in j in jx, maybe I in j. And for k non-negative integer, I write x bracket K to be the disjoint sum, disjoint union of the xj's, where the cardinality of j is k plus 1. This is in the literature, I think there is two versions at least, but I prefer this notation. So, and we call this map a small k. Okay, under this condition, we want to consider the weight spectral sequence which relates the log crystalline cohomology of x big log over s small log and the crystalline cohomology, relative crystalline cohomology of xi's over s with trivial log structure. And the complex is called, relating this, is called the sometimes p-adic Steenbrink complex, or maybe I should put Hyodo Steenbrink complex, or but if I put Hyodo, then it's natural to erase p-adic, but I don't know. Okay. And this is constructed in Mokrane and 93 in some cases, and in this setting, this is due to Nakkajima on archive in 2019. And so, and I explained the construction, but for simplicity, I assume this x big log to the s small log admits, and we had a carry s small log, and I assume that it admits a carry x big log, which is log smooth. And this need not be Cartesian, but and this is exact closed immersion. Exact means the log structures of carry x and x are the same. And then it is true locally always, but if we would like to work in a general setting, then we should take open covering and take a check covering associated to that. But I want to do that to avoid. I don't want to do that today to avoid the complexity of the notation. And then we have the D big log. This is the PD envelope, log PD envelope, but it is the exact closed immersion. So this is a log PD envelope with this log structure. But anyway, log PD envelope of sorry, iota. I forgot to write this by iota. And then we have the drum complex, log drum complex, D big log over S. And this is O carry D tensor O x of the O omega dot x big log over the carry S. And this is a PD drum complex. And this complex is endowed with the filtration, which I write by pk omega dot d big log over carry s, endowed with the filtration called the weight filtration. Weight filtration. Defined by the number of d logs. This is very rough, but anyway. So, and the point here is that the differential drum complex is considered over S, not S log.
So you don't kill d log of the parameters downstairs, is what you mean.
Right, right. And then Aij is defined to be the omega I plus j plus 1 of the Curry div big log over Curry S divided by the Pj and Pk Aij. I wrote the filtration by the capital letter P following Mokrane and Nakkajima, and this is just, and because I'm in France, so the filtration power, so weight filtration. And then this is a 2j plus k plus 1 plus pj, more precisely, plus pj divided by pj. So if this is smaller, then it's 0, and if this is bigger than this, and then this is non-trivial. And this is 4k is integer. And then, as Professor Levin said, we have that theta d log 1 lives inside omega 1 of Curry S small log over Curry S, and we write its image in omega 1, in our omega 1 by the same letter, same symbol. Then we have two morphisms. One is the usual derivation, and another is theta wedge, taking the product with theta. And this is a well-defined map like this, and preserving the weight filtration. And then I defined A dot P to be the total complex of A double dot P. Maybe we should replace D by minus D, but okay. I don't care so much today. So yes, I'm sorry, but and this is a p-adic Steenbrink complex of Nakkajima. I remark that Mokrane, it is first constructed by Mokrane in the case where S is spec K, spec kappa, a perfect field. Of characteristic P, and Curry S is spec of W and kappa. And this the construction is not exactly the same as this one, but he used instead the log Durand-bit complex and its variant, Durand-bit complex.
But when you say total complex, you have 2 dots on the A, but you only have the 1 differential. You use both differentials for the double complex, or just?
Sorry, we use total complex is written with 1 dot. I'm sorry. Okay. Dot. I'm sorry. I'm sorry. No, it's not. I don't mean this by D, but this by P. I'm sorry. It's a fit.
Okay.
I'm sorry. Very sorry. Okay. So,
sorry, I just want to check something. So up until now, do you really need that it's a log structure, or it also works for pre-log structures?
sorry. Sorry, I couldn't catch it.
I mean, up until now. I mean, whether everything works for general pre-log structures or
Pre-log. I don't know, but
Okay, we can.
no, I'm sorry, but I don't know. But pullback is first. For example, pullback should be the log structure, no? The pre-log structure.
But the relation between Mokrane and your construction is actually if you reduce Mach P, the Mokrane Mach P.
Oh, the compatibility is also work contained in the work of Nakkajima. So yeah. I think it's more or less yes, more or less a proof of the drum beat to crystalline comparison. I think. Okay, and then to compare this and for k, index k, I had x curly k, but in the same manner, we can define curly xk and curly dk, which is a PD envelope, and omega dot curly dk over S, and this is a PD drum complex. And then one of the theorem of Mokrane and Nakkajima is the first, this complex computes the omega dot curly d big log over curly s small log. So here is a difference with the previous complex. And the second is the computation of the graded pieces. Graded piece of this is, which this is a sum with some indices of the A lower star 2j plus k of the omega dot, I'm sorry, that d 2j plus k over s of them, and we'll shift minus 2j minus k, if I'm correct. Oh, yeah. And the point is that this is related to the log crystalline cohomology, relative log crystalline cohomology of x big log over curly s small log. And this is related to the crystalline cohomology of xk over curly s with trivial log structure. So, and this complex induces a weight spectral sequence of whose even term is a crystalline cohomology and whose limit is a log crystalline cohomology. And but I don't have much time, so I omit to write the spectral sequence itself. But and now I explain my motivation. So that's all. So then what I should do, I would like to do is the following observation. We have the map U, usually noted by U, from the crystalline side of X to crystalline topos of X to the Zariski topos of X. And we regard it as an analog of the X analytic to X Zariski, so in the case of C. And if we consider like this, then there should be certain weight filtration here on analytic side, and then which gives the Zariski side, on the Zariski side, the complex, p-adic Steenbrink complex of Mokrane and Nakkajima.
Sorry, what do you mean in the direct sum? J at least 0 minus k?
J is bigger than equal to 0, and J is bigger than or equal to minus k. Okay. I'm sorry. Max 0 minus k. You more precisely. Yeah. I'm sorry. So my question is there a filtered object on a certain crystalline site which gives this A dot P if we apply R U lower star. So I explain the construction. Construction is, in some sense, the construction is the same. So we factorize the morphism F from X big log to S small log. And new log scheme is X small log. This is the X endowed with a log structure which is a pullback of that on X. And another one is X very big log, which is a fiber product of X big log and X small log with trivial X. And this is, X and the log structure associated to the M direct sum N. So here is my rule. So if something is related to M direct sum OX star N, I will write it big L, big O, big G, and I will sometimes call it a very big log. And then we have X big log to, we had a map from X big log to S small log, and this factors X small log, and then by using this fiber product definition, then it factors to X very big log. And I will write this by psi epsilon, and here by psi, as the symbol suggests, this is nearby cycles. And then we have our for simplicity hypothesis. We have also the carry X small log and big log. There was that, but we also have the carry X small log and carry S very big log. And of course, by taking the PD envelope, we get these. And I'd like note that omega dot we had omega dot, we consider omega dot to carry D big log over S with trivial log structure, but this is actually equal to the omega dot to carry D very big log over carry S small log. And in the following, I want to work over carry S log, not over carry S. So this is one reason that I use this very big log. Very big log. Okay, and
I have a question.
yes.
Why do we have a map from a medium log to the very big log?
Because we have a map from map from X log to big log to small log. we have a natural map from big log to small log, and by using this fiber product. And an observation is that because the graded pieces of our complex should be related to the usual crystalline cohomology, so by this observation, graded pieces should be related to the xk over s, but because we would like to work, I said that we would like to work over curly s small log. So this should be related to something on the xk small log over curly s small log. So from this observation, our object would be on x small log over curly s small log. Because by pushing something on by a star, then it should be, this is a place where a dot lives, a group of a dot lives anyway. So, but there is one point which is very bad, is that x, this small log is not log smooth. In any sense, it's not smooth over s log. So it is not good to work over x small log s small curly s small log. So, but an idea is work over the system of xj's. So we define the crystalline site on x small log over s small log. It's a kind of modification of our crystalline site CR as object of this category would be an object in xj log over curly s with small log crystalline site. This is actually smooth, log smooth, actually smooth. So, and for some j. Well, we may say that I consider simply shell log crystalline site. And morphism is natural, so I omit it, I'm sorry. So I don't have so much time. So, and then, but still there are problems. So we have the following diagram. We have x big log, x very big log, and x small log. And I decided to work over xj's, so xj small log, and by pulling this back, we get x big log j and x a very big log j and x big log j. This is a exact closed immersions.
So in principle, it might depend on the choice of the covering x side, or.
Yes, I think so.
So it's, okay, you're right. So actually, it's not only.
Oh yes, yeah.
So why is it an inclusion? I thought the.
For example, but the base is trivial. Generally, this is a canonical irreducible components. But for example, if S is a spec of the infinite product of the fields, then I don't know the canonical way to decompose. so it depends. But if S is moderate, Noetherian integral or something like that, then and smooth or something like that, then there should not be this decomposition should be is made to be canonical. So okay, so but the problem with this is that if we work over here, then it is inevitable. It seems to me that inevitable to work over this, but this is not log smooth. This is log smooth over S small log, but this is not, and not log smooth over S small log. And then we need the following, but with natural structure of idealized log schemes. Log scheme with the ideal of sheaves, certain coherent ideal of sheaves on the monoid, sheaf of monoids. And then they are ideally log smooth. Yes. And I'm sorry that these three schemes have a carry X version in our local setting. And D also. And these are also with idealized log scheme. Yes, yeah, I should write August. I should not have erased maybe, but okay, so here. I write the same, very similar construction here again. Then there exists a linearization factor. Which is standard in the theory of log, crystalline side, crystalline cohomology. And this is because we work with the modified version, so the input is a compatible family of all DJ modules. And the differential operator is a PD differential operator. On DJ, I'm sorry, DJ, yes, DJ small log, yes, small log over carry S small log to the category of all modules. O is a structure shift, but I don't want to specify because there will appear many O's, but on our crystalline side. And then we define the carry L big log, very big log, to be the image of the dislinearization factor of the Mokrane and essentially the Nakkajima's complex. DJ big log over carry S small log, and this forms a family with respect to J, and we get some object here. And then the construction, the rest is similar. Carry A dot J to be the truncation, canonical truncation by J bigger than or equal to J plus 1 of carry L a very big log, and I think shifted by J plus 1 and the curly pk curly a dot j to be the weight filtration. This is tau from j plus 1 to 2j plus k plus 1 of this L very big log and j plus 1 shifted, and then we have theta, and theta defines yes, a dot j p to the a dot j plus 1p. Maybe we should control arrange the signs, but anyway. So then we get that a dot with p to be the total complex of a dot dot p. And this is a, so this is a, I emphasize that this lives on our version of crystalline side. And the theorem is, in some sense, theorem holds as expected, but with some modification. We also have x big log over curly s small log CR variant, x very big log s curly s small log CR, x bracket k small log over curly s small log CR, and moreover, we need another site, which I call x, no, I'm sorry, x, we had a x small log over s small log CR, but I need also its restricted version, which I write RCR. The object of here is an object in x small log j over curly s small log restricted crystalline site, which is given in a paper, in a book of Bertero. And restricted means that it is that the object should be associated with some exact closed immersion to log smooth objects over the base.
So probably you have already explained, but can you tell me what the topology is on this?
Zariski topology. Topology of what? Crystalline site? Zariski covering. Zariski covering of the object. p-adic.
But J runs over various.
No, there is no covering between the objects.
So what's the difference between just taking from disjointing or something?
No, because xj intersect xj prime is xj union j prime. So. And then we have the following diagram, but I'm afraid I can write this diagram. But so we have the x big log over s small log CR to the x very big log to the small x C. Yes, I can. I think I can work also a simplicial setting. Yes. There's no much reason that and then I have a map of AK from the xk log over s log CR, and here we have the functor q morphism Q, morphism of topoi Q from RCR. The point of this Q is that this L log factor, log linearization factor is not exact, which is known not to be exact, but if we compose with Q upper star, this is exact. Oh, I'm sorry, I forgot to write the name of morphism. So this should be epsilon, and this composition is written by psi. Then result is as expected. So but we need Q in many places, Q upper star. So Q upper star A carry A dot is isomorphic, quasi-isomorphic to the Q upper star of the R psi lower star of the O. O is a structure crystal. And so this means this is the analog that this A carry A dot computes the log crystalline cohomology. And then second thing is that Q upper star of the GUR of the
from the restricted to the non-restricted.
Ah, yes, yes, yes.
And this is J bigger than 0 and minus K of the Q upper star of the yes, A 2J plus K lower star O minus 2J minus K. This is our version that the graded pieces computes the crystalline cohomology. And then third one is, oh, I forgot to write U, but U is projection to the Zariski site. And then if we apply the filtered direct image, then this I get the p-adic Steenbrink complex of Mokrane and Nakkajima. And the result itself is not, I don't think it's so surprising, but because we just upgraded everything to the crystalline site. But the proof is all interesting to me, or at least to me. The crucial point is the Poincare lemma. This says that R epsilon star O is quasi-isomorphic to this L our linearization. And this is this means that the structures in classical Poincare lemma says that the structure sheaf is resolved by a linearization of the drum complex. And this is our version, but we need to push it down to epsilon star. And actually, I forgot to say that in the case of smooth schemes with simple number crossing divisors, this idea and the proof is done in my book with Nakkajima on which year? On which year? I don't forget. 2008.
So what's the R-Chris?
Our R-Chris is a full subcategory consisting of the pair UT such that T is a PD envelope of the something log smooth over S log. Yes.
Wow, it's for restricted, maybe? Restricted
Strict.
restricted crystalline, like in Berthelot?
In the case of yes, usual crystalline site, it's due to Berthelot, and also in logarithm case, we can find it in some paper with Tsuji-san. Yeah. And my book with Nakkajima also. Yes. And so the point, and if then this means that this A dot is something tau. I don't want to write so completely, but this is not an exact description, but A dot is something related to R epsilon star O. And then by using this Poincare lemma, and also actually there exists a variant for R psi star O, and of course AK star O. But by using this Poincare lemma, we can prove that this Q upper star R psi star O minus 1 to the Q star R epsilon star O and R psi star O plus 1. There exists some triangle, and this triangle induces an exact sequence that 0 Q lower star R K minus 1 psi star O to the Q upper star R K epsilon star O to the Q upper star R K psi star O and 0. And if you have read the exposé de Professor Illusi on period p-adic or a paper on Professor Illusi on Drock conference, Drock trimester book, yeah, we can find, or a paper of Rapporto Zinc or a paper of Takeshi Saito, then we see the same, really the similar exact sequence. And then actually, if we know this, and then by some computation, then we get to the first part of the theorem, but I don't have enough time. And the second is also a consequence that the following proposition coming from the computation of the drum complex, linearization of the drum complex, RK epsilon star O is actually quasi-isomorphic to the A K minus 1 star O. I don't, perhaps, yes, this is, okay. This is quasi-isomorphism as Thebes, so, hi, yeah. Then, by using this, we get to the, also the second, and the third is, third I omit it. And so the important thing is that this claim A and this claim B and this claim C. And it really appears in, yes, in the construction of p-adic weight spectral sequence, and of course Becci, but I don't know much about Becci, so I prefer to say p-adic, but yes. And then it suggests another construction, which is still work in progress, but so this A defines N from the Q upper star RK psi, R psi star O to itself. This is a monodromy operator. And B and C, if we have the property and B and C, I think should imply that as in the erratic case, due to Takeshi Saito, this Q upper star R psi lower star O is perverse, shifted perverse, and shifted perverse object. I think that it would be good to define the perversity on each PD thickening, but I have not checked it carefully. So this is my expectation, that it's a shifted perverse object. Sheaf. And the filtration is the monodromy filtration. The filtration on associated to N. And then if this is the case, I think I have the small application that on the expected small application would be the multiplicativity of weight of the Mokrane and Nakkajima's object. So, because I think Q upper star R psi lower star O and L tensor itself, and then goes to the R. I expect to construct the filtration here, filtration, a filtered map like this, and then if we push it down by the RU lower star, then RU lower star, no, I'm sorry, Q RU circle Q lower star, but I think, but it is known by Berthelot that this Q is harmless. So then we get the multiplication of A dot P. And it is, in some sense, interesting because Aij was omega I plus j plus 1 divided by pj, and this 1 is harmful, and I don't know how to put a natural multiplicative structure on this complex, so this may be a possible application of my construction. So thank you very much.
Thank you very much. Are there any questions or remarks?
So do you have a definition of perversity in this? Yeah.
Yes. So I feel that we have a PD thickenings, so and with certain stratification, so stratified certain stratification. So I think naively just to use this.
No, but this is more like coherent setting. I mean.
Yes.
I mean, even without log structure, do you have a reference, for example, in the simplest case?
I think that somewhere in BBDG should work, but I don't know.
What is the question?
Definition of a power structure.
Yes,
T
I
structure.
had the same question.
I thought that, but for each UNT, an object, it had
Gaber's general formalism, maybe? Or
yes, I think.
Or general formalism, which would cover this sort of situation, which is not erratic or p-adic.
Not erratic, but
but anyway, maybe.
Yeah.
So you need some geopostar, something like that.
Yes, but this is performed on each thickening, PD thickening. Yeah.
So I also have another question. So here you are using some well, technically I'm not following, but here you're using some sort of a linearization of differential operators, which some sort of original approach of Grondig and Berthelot. But this crystalline type comparison, this many years ago, this Bart de Jong's new approach, does that apply to your situation?
Could be. Yes, maybe, but I think that would also give the same result of same types, because we need to put a Q upper star. We how to say, without Q upper star, I think this is false. So yeah, I think this would lead the same conclusion. But okay, anyway.
Questions? I had some small comment. So this Steenbrink complex is quite bizarre, right?
Sorry.
So it's supposed to give you a formula for upside. Formula for upside starting with what? So you have the piece of the omega log, right? So they are not upside, they are RJ star. So upside is RJ star taking invariant of the inertia group, right? So how can you concoct before taking invariant upside from RJ star? So in the complex case, there was a very curious formula but it never was now. So you take RJ star above, right? With, now we would say multiplicative structure and Dirac algebra structure. Above the RJ star below, also Dirac algebra, and you take tensor product with the Dirac tensor product with the constant, and then you get upside.
Okay. Yeah.
This is somehow gives the flavor. So this is somehow a displaying of this formula. Nevertheless, now that Steenbrink has concocted with the multiplication by the sum of the over the excitation.
But
D log xi.
But Luke, this formula it only works with unipotent monodromy, or
what?
This formula for nearby cycles you were describing only works for unipotent monodromy, maybe?
No.
Oh, really?
Yeah, I think so. I think so. Yes, that's. We can discuss a little bit more. Yes, as far as I remember, it is long ago. But I was struck by this formula. Yeah. So derived tensor product over derived cumulative range RJ star from RJ star to upside. So and about purity, you don't have. There is not much. Purity of monodromy.
No. I'm sorry.
Yeah, sorry. So I think we should start again maybe 20 or 25 maybe.
Oui,